welcome you all to this course on defects in material. In the last class, we looked at how to visualize intrinsic striking fault. Today, we will try to look at how to visualize extrinsic striking fault, okay? And then we will also consider different types of reactions by which a perfect dislocation in an FCC lattice can split into partials, okay? And the interaction of these partials which are moving in the same slip plane as well as in other slip planes, in different slip planes, their interaction, we will look at it. And the last point which I would like to concentrate today is on the need for Thompson Tetrahedron and how it helps in understanding the different dislocation reactions, okay. This is all we would like to cover, okay. Because we mentioned in the last class that if you look at this picture, this is an A layer and that atom which is there on a B layer. This B layer atom, if it moves from here to here or from here to here or here to here, generates a striking fault. So this vector is specific. If we consider movement of this atom from here to this position or in this position or in this position, which is essentially nothing but the reverse of these directions, that will lead to essentially a high energy fault, okay. That is what is expected. Or what will happen is that this atom, this B atom will be brought to this position which is on top of A, so it will generate a sort of a hexagonal lattice, okay. This is essentially, whereas here it moves from here to here, this position it comes to a position which has got the same energy as the position which is occupying, but only it changes the striking sequence. That is what an intrinsic striking fault is. We will try to understand how a movement of atom from here to here and an extrinsic striking fault, they are equivalent, okay. So here what I had just shown is that what are the different perfect lattice translation vector directions which are being shown, okay. These translation vectors also can split into partials, okay, and depending upon the direction, which one will create extrinsic striking fault, which one will create intrinsic striking fault, we will look at it just after some time, okay. Okay, you look at this striking of this layer which is being shown. This is a atom which is shown large, it is the A layer. Atom on the B layer is shown here, and this is the position C layer, where if an atom which is sitting on this A layer in B position, if it moves from B position to C position, that will create an intrinsic striking fault. Here I had shown, okay, just the one particular section of a Thompson tetrahedron, or essentially what I had shown on one plane, what are the different directions corresponding to perfect translation vector as well as partial vectors. If you see from here to here, this corresponds to a vector moving from here to here. A vector from here to here, perfect translation vectors, is one moving from here to here. The one from here to here represents the vector which moves from here to here, okay. And then a vector from here to this center, or a vector from here to here, or a vector from here to here, they represent all the partial vectors, okay. That is what essentially is being indexed. So by a movement from B, that is if you have to move an atom from B to C position, okay, essentially we have to move, okay, that translation will correspond to, okay, a vector which is 1 by 6, okay. This direction is 1 by 6 to 1 bar 1 bar, opposite of it the reverse direction, so it will be 1 by 6 2 bar 1 1. So if we give 1 by 6 2 bar 1 1 a translation, it will be moved from here to this particular position, okay. Now that is what is being shown in this slide. When the translation has been given, the B atom has been positioned, so the B site is there. Those atoms which were there at B site now has come to the C site, correct? Then when that come to the C side, what is going to be the stacking sequence? It is ABC, ABC, okay. After A, then the C comes, then ABC, like that the stacking sequence will go. Now next what is being done is that, now if you look, this is the C atom position, the A atom position is below it. So in between these three C atoms, A atom is occupying a position. That is the layer below the C layer, okay. And this is the B atom positions, that is B side positions, okay. If this A atom, this atom which is sitting at A position, if I shift it from here to here, okay, that will involve a translation vector 1/6 112 bar, okay. You can make out from here that when I give that translation, okay, then what's essentially going to happen is that this A atom comes to this position, B position. That is what essentially is being shown here, okay. Not only that atom, that shift is given to all the layers which are above that also, A layer. So all that, so this A atom comes to this position, then the C atom which is there, it will also shift to a new position, okay. That is essentially what is being the stacking sequence which is being shown here, okay. That ABC, ABC, that A position, okay, the B, C, A. Now you can change, no, I think, yeah, this is the position, A, B, C, B, C, A, C, A, B, C, A, correct? This is what this position corresponds to. So now it has reached a position, okay, which is essentially a fault which is there existing on two layers. And this reaction, if we now try to look at it, here what we have given 1/6 2 bar 1 1, this is on the above the A layer, this is the translation which is given. Now below the layer and above we had given a translation 1/6 112 bar. These two together will give rise to a translation 1/6 1 bar 2 1 bar, 1 bar 2 1 bar, okay. 1/6 1 bar to 1 bar is from here to here, correct? That is essentially nothing but from here to this position. That is from here to high energy position, the B atom, the atom occupying B site is moved from this position to this position is by this vector, correct? 1/6 1 bar to 1 bar. So essentially what we have done is that by introducing intrinsic stacking faults on two layers, okay, so the atom is being moved from one position to an identical position only, okay, though only an extra surface is being created. By doing this process, we are able to generate, that is, we are able to give it to the lattice an effective movement of atom from one position to another, which is equivalent to from here to here. This is how an extrinsic stacking fault is generated, okay. In fact, the same thing I had now just shown, what I had shown with respect to a figure, because there 1 layer we were looking directly at the different layers, okay, along 1 direction. Now we are looking at these layers. What we have done is essentially the layers are, this line represents a cut section of the layer, okay. The layers are perpendicular to the screen, okay, all the layers are going like this. So this is the ABC stacking sequence, okay. Movement of a partial by this, okay, above this it changes from B position, it moves to here, that is by this vector 1 bar to 1 bar. If it moves, it will bring A atom to an A atom position. So this movement of a partial here will move all the atoms above also by the same sequence of shift, and that gives rise to this sort of a stacking sequence. So this is essentially a high energy position which is not allowed. So instead, what we can do, what we did in the last case also, that is in the previous slide also, as I explained, the B atom that is above this layer B atom is shifted to C position. So this is how the stacking sequence have become CA, CA. It creates only an intrinsic stacking fault. Now the layer above A layer, I had moved it from here to a B position. Okay. By doing that, and not only that, when I move it here, all the layers above also will be shifted by that same way. So when that shift is implemented, the C will move to A, this A will move to B, okay. B will, because it is A moves by one dislocation which has moved it here, and the next dislocation in the another plane, when it moves it from here to here. So now the stacking sequence has become CBAC like that. This sort of fault which are created are called as extrinsic stacking faults. Okay. The same reaction is given here. Okay. But what is important about this stacking fault is that the energy of this fault, since it involves movement of atom in two layers, more energy has to be spent. Okay. The stacking fault energy is roughly 1.5 times to 2 times that of the intrinsic stacking fault energy. Okay. That is what the observation is. So far we considered the change of stacking sequence. There is another way the change of stacking sequence could be considered. I am showing it various ways of perceiving the generation of the same extrinsic stacking fault. Okay. Here what I have done it is, I have just written the stacking sequence. This is a stacking sequence in along 1, 1, 1 direction in a perfect lattice. Okay. Now at this particular point here, the B positions are all there. This B is shifted to an A position. If I do it, the translation of B position because above A, there are two options are there. B can be shifted to C position or B can be shifted to an A position. If we shift it to A position, it gives rise to a high energy fault. Correct? What is the another way in which it could be done? You look at this stacking sequence. In this stacking sequence, if I introduce between A and B another A layer, that will also give rise to the same type of a structure. That is either by shift of an atom or by introducing a layer also, we can generate the same type of a fault. But this again will also be a high energy stacking fault. Correct? Because here we can understand something much better than the way it has been shown in because the earlier micrograph, when you show with respect to the atomic positions, okay, layers, the different layers, then the advantage is that we can see the vectors and understand how the vectors change. Here we are just looking what the stacking sequence which has changed, only looking at the stacking sequence. Okay. In this or in this structure, whatever be the way we have generated, this is what essentially is the stacking sequence which has formed. To restore order, we have to introduce 2 atomic layers, correct? Then the order could be restored. Whereas if you remember in the case of intrinsic stacking fault, if we introduce 1 extra layer, that is good enough to restore the order. Here we require 2 layers to restore the order. Okay. And the fault vector also, if we try to find out, essentially corresponds to nothing but how many layers have to be added or subtracted. So in the case of an intrinsic stacking fault, since 1 layer has to be added, okay, the stacking fault sequence, if you look at it, okay, or if you remove 1 layer, that is the vector of the defect which has been generated. So the fault vector for intrinsic stacking fault, we can write it as 1/3 111 type. Here the fault vector will turn out to be, this is for intrinsic stacking fault, this is for extrinsic stacking fault, correct? This is essentially we considered as a high energy fault, which normally does not occur, that sort of a movement. Okay. What is the way in which it can be done? Instead of adding, we considered one way in which shifting of atoms on 2 layers, we can create the extrinsic stacking fault, which is equivalent to moving an atom from one position to a high energy position, correct? that we have considered. Now we are looking at another way. The other way is that if we add one more layer to a perfect stacking sequence, but now it is not between A and B, between A, B and C, okay, or between A and B, instead of adding a A layer, if I add a C layer, then what will happen? The stacking sequence will become ABC, ABC, CA, CBA, okay. This now becomes the same as by creating intrinsic stacking fault in 2 layers, how we achieve the extrinsic stacking fault, the same stacking sequence comes, okay. Because you see here we added between A and B, okay, another one layer, but in position which is an A position, okay. Now what we have done is between them we have added another layer on top of an A layer which is essentially in a C position, okay, because all other layer atom positions remains the same, okay. This produces the same stacking sequence as produced by extrinsic. You can see it here. This is ABC, ABC it is there. I am showing just one half of it, okay, that loop. You look here. Here I had added one layer partially, correct? When this layer has been added, okay, the rest of the layers remain the same. So now if you look at the stacking sequence, it has changed. It becomes the same as that of an extrinsic stacking fault. This type of fault is nothing but an interstitial fault. That is, by adding one extra layer in between, we can generate interstitial loops. Okay, interstitial loops are nothing but an extrinsic stacking fault, right? So essentially, if I take a mirror reflection of it, the other part would have come. That is what it would have been, a section of the fault, okay. In this fault also, I have to add 2 layers, that is corresponding to between A and C, one layer has to be added, a B layer, okay. Between C and B, one A layer has to be added. So if I add 2 layers, I can restore the order. A perfect lattice could be generated, correct? So this extrinsic fault which is generated also is equivalent to, now you can see that in both the cases, by addition of only 2 layers, whether the atom is shifted from one low energy position to a high energy position, or by creating fault on 2 layers, to restore the fault, essentially 2 atomic layers have to be added to restore the fault. So the fault vector will turn out to be, as I have mentioned, the same value. Is it clear? Let us consider, okay, some possible dissociation of dislocations into partial, because what we have considered is how a movement of a partial dislocation generates fault, okay. We know that in a material, okay, whose stacking fault energy is very low, okay, the dislocations would like to split it into partials. That is the first tendency which dislocation will have, because when it splits into partial, okay, overall there is a reduction in energy of the system. Instead of remaining it as a okay, bar 1. That is, this dislocation, no, this is 1, 2 bar 1. If you add both of them together, this will become 3, this will become 3 bar, and this will become 0. This is correct, okay. And what is going to be the B squared value here? It's essentially half. Here it is 1 by 6, here it is 1 by 6. So because of this reaction is permitted, because the stacking fault energy gets lowered. correct? When the striking fault energy gets lowered, that's one part of it. The other part is that these two dislocations essentially are in an orientation, okay, where a repulsive force acts between them. If you try to calculate the force between these two dislocations, it will be repulsive. That means that this dislocation will try to move apart, okay. But when they start moving apart, the dislocation is present here and it splits into a partial, two partials with a region between them, and assume that this width of this region is extremely small, even smaller than initially when they have started splitting, smaller than that of the Burgess vector, okay. Then when it tries to split, some surface has to be created because a fault is created in between. Striking fault is created between these two partials. That means some fault is created, means some extra energy is required to create that surface energy will be required. That surface energy is balanced by the gain in energy which is going to happen between this dislocation splitting into partial. Now what is going to happen is that if the striking fault energy is very high, even at a distance which is very small, the gain in energy is being balanced. If the striking fault energy is small, the separation between the partials can be large, so that the width of the dislocation is quite large, okay. That's what it will happen in the case of low striking fault energy material, okay. So essentially, these are all the reactions by which the dislocation can split into a partial perfect dislocation, and this reaction which we have considered is on one-on-one plane. Let us see what are the types of partials which we can create in one-on-one plane, okay. These are all the type of partials which we can create in one-on-one plane. This will all be 1 by 6 because these are all perfect translations. So this is going to be the Burgess vector of the partials, okay. These partials, okay, we can try to look at, suppose we have one partial which is there 1 by 6, 1, 1, 2 bar. It interacts with another partial 1 by 6, 1, 2 bar 1. What will be the net resultant one? 1 by 6, 2, 1 bar, 1 bar, correct? So here if we consider it is 1 by 6, this is also 1 by 6, so total becomes 1 by 3, here it is 1 by 6, so this reaction is possible, correct? Let us look at that same reaction, this reaction, but the Burgess vector of one of the partial is reversed to 1 bar. Now what is going to happen is that this will turn out to be half 0, 1 on bar. Now the B squared is 1 by 6, here it is 1 by 6, here it is going to be half. So that means that this reaction is not possible. That is, a dislocation, perfect dislocation can split into partial, but a partial dislocation, if they have to join together and form a perfect dislocation, it will not happen under equilibrium condition. We have to apply a lot of stress to make these two dislocations join together. This is the take home point from this reaction, okay. So that means that energetically this reaction is not possible. Then let us consider interaction between partials. Now we have considered interaction between partials which are lying in the same slip plane. Only this type of reaction will happen, whichever be the combination which you consider. Suppose consider a partial which is lying on another plane, 1 on bar 1 also. Okay. A similar reaction we can write it. Okay. Then we can find out different combinations, okay, which will give rise to, okay, energetically favorable reaction which we can find out. Correct? That part of it, because there are many reactions will be there, okay, many types of possible Burgess vectors of dislocations will come, partial dislocations. That part of it I would give it as an assignment which you can work it out and find out what are the possible reactions which gives rise to, okay, which are possible, and energetically possible, which are not energetically possible. But I will consider a case where a reaction which is possible, okay, in that case when the dislocations interact, okay, what is the sort of a Burgess vector of the dislocation which is being produced as a result of this interaction. Okay. This what I have done it is taken the case which we have considered earlier in the case of a perfect dislocation, where perfect dislocations moving in two slip planes which have interacted together and formed a Lamar lock. Okay. Now we assume that since the stacking fault energy of the material is low, this dislocation is split into partials on each of these planes. Okay. The reaction by which this dislocation can split into is given here. Okay. And the reaction by which this dislocation can split, energetically favorable reaction by which it can split, that is given here. So these are all the two partials. Okay. Let us look at these two partials. Okay. This dislocation is moving in this direction, this moves in this direction. When they come and interact, okay, the net sum of these two interactions, what it will turn out to be, this is 1/6 1 bar 1 bar. This is 1, right? This is 1, and this will turn out to be 0. Look at the self energy. Here it is 1/6, here it is 1/6 is b squared, and this will turn out to be 2/36, correct? So it is 1/18. So here it will be this plus it will turn out to be 1/3. So this is small, so this reaction is possible, correct? But if since by interaction of these two dislocations, a new dislocation has formed, that dislocation's line direction has to lie in the intersection between these two slip planes. The intersection between these two slip planes, the line direction will be 1 bar 0. Okay. So, but the line direction and the Burgess vector are perpendicular to each other. That means that this dislocation is a H dislocation. If it's an H dislocation, then U cross B will give the slip plane. The slip plane will turn out to be 0, 0, 1. That means that this dislocation is going to lie on a plane which is the density of packing is very small. Okay. In such a case, the friction stress is very high. So this dislocation is a sessile dislocation. Okay. This sort of lock is called as the Lamar-Cottrell lock. Okay. There is another name also is being used, which is called as a stair rod of dislocation. Okay. Why it is called as a stair rod is that is a dislocation which has formed here. One dislocation has come here. There is another dislocation is there. These two are also two partials which are there. The other two partials have joined together and formed a dislocation here, right, with a Burgess vector like this. Now, this looks like a staircase, na? That is, you have a staircase in which, you remember that in a staircase when we put carpet, what do? To hold the carpet in place, we put a rod so that the carpet can be kept in a staircase like this by putting a rod here and anchoring it, right? That's called as a stair rod, okay? For the stairs we put it. That is the name which is being given to this sort of dislocation. Is it okay? Clear? Okay. So, we have considered the energetically possible reaction which we have considered. There are many other reactions which one can consider like this. There are many types of, each of the reaction give rise to different type of partial dislocations. Some of them will be a stair rod dislocation, and most of them are going to act as obstacle to movement of perfect dislocations. That is what is that is what it adds to the dislocated forest of dislocations. Okay, any dislocation which has got a low, even a perfect dislocation, if it is lying inclined with respect to a slip plane and the result shear stress in that plane is small, that will also act like a perfect dislocation. So there are many dislocations with different type of Burgess vectors can be there in the forest dislocation. These dislocations also add to it. Okay. Yeah. Another example which I wanted to take, the other one is that we consider the stacking sequence, right? Just looking at the stacking sequence, we found that how an intrinsic stacking fault can be formed, how an extrinsic stacking fault can be formed. Suppose I form an intrinsic stacking fault on every layer. Okay. So what has been done is that this B atom has been moved to C position. A stacking fault is created now. CA it has come. Now the atom just next to it, that's this A atom, is moved to B position. So I create another intrinsic stacking fault. Okay. So this has become CB. Then the atom next to B, this C, it is moved to A position. So it creates another intrinsic stacking fault. Now if you look at it, the stacking sequence has become CBA, right? And then if I can move B to another one, okay, this B is being moved, so it becomes C. Now if you look at the stacking sequence CBA, like that it becomes. So across this plane, okay, the stacking sequence on this side is ABC, this side is CBA. One is a mirror image of the other, okay. That is, by moving partial dislocations, we generate intrinsic stacking fault on every layer. We can create twins. These sort of twins are formed in materials which have got low stacking fault energy during deformation, and generally the name which we use to describe them, or we call them as microtwins. This terminology which you might have seen in many papers, they say that microtwins do form. Just let us consider the case in which not in every layer but every alternate layer an intrinsic stacking fault is created. So here what we have considered an ABC stacking sequence, okay. Then this C layer is there. After this C layer, okay, ABC, this is ABC, this B layer is moved to C layer, then this layer will move. So this is how the stacking sequence is. Now what I do it is that this layer, B layer, this is a layer, this is the next layer, this is being moved to another layer, okay. That is not this layer, I said alternate one. Alternate one means that you leave this and come to the next one. So this B layer is again shifted, then it will go to a C position. This is how the stacking sequence. Then the next alternate one, if I move it, then this B layer will come to a C layer. Now if you look at the stacking sequence, this is ABC. Now we are able to form CA. That means an AB type of a stacking sequence. This way, by creating overlapping stacking fault, but creating stack fault not on every layer but on every alternate layer, we can generate a hexagonal closed packed lattice, or hexagonal closed packed lattice itself can be considered. That is, formation of hexagonal lattice can consider they are related by a defect structure. That is, by generating stacking fault in FCC, we can generate HCP structure. There are many structures are there in ordered alloys where, or in disordered alloys, by generating either stacking fault or in the other case antiphase boundaries. Okay, that is the fault vector which is not a vector in the real lattice. We can generate another structure. Like when here itself, we can take another example. We considered the stacking sequence like ABC, ABC. Okay. If I move this B layer to an A position, this will become B, this will become C, like this it goes. So this, if you see it, AA means that is hexagonal. The arrangement of atom in each of this plane is hexagonal. One on top of the other creates a simple hexagonal. That is, so this is also another type of a transformation. Right? So any partial vector in a lattice will generate, okay, another lattice. So these lattices you can consider it, that is defect related lattices, which we can generate this way. Okay. What are the other type of reactions which we can consider? Okay. So far we considered partials, and these partials are called as Shockley partials. That is, all partials 1/6, 1/2 type are called as Shockley partials. Okay. 1/3, 1/1 type, they are called as Frank partials. Okay. Then 1/6, 1/10 type, these are called as stair rod. Okay. There are 1/3 also, there are many are there, different names are being given. Okay. Suppose here we are considering a case where there is a partial, there is a Frank loop is there, it is lying on 1/1 plane, correct. This one is a partial, okay. This is also lying on 1/1 plane, and these two partials interact. What happens? They generate 1/2, 1/10, correct. That means that the fault is removed, because this dislocation has become a perfect dislocation. But in which plane this dislocation will be lying? Okay. This gives rise to half 1/10. Here both the dislocations are lying on 1/1 plane. Okay. This dislocation is going to lie on either on 1/1 or 1/1 plane, correct, because the Burgess vector should lie in the direction should lie in the slip plane, and that means that the resultant dislocation have a Burgess vector which is in plane, and energetically this is 1/6 b squared. If you consider here, what is the value, it will be going to be 1/3, and this is going to be half. If we add these two, 1/6 plus it is 2/6, correct. This will be essentially going to half. Okay. So this reaction is that there is no net gain or loss on energy, but still this reaction can occur when we applied load. Okay, because load can tilt the balance of the reaction. It can supply the energy which is required for these sort of reactions to happen. That means that during deformation, if these sort of faults which are formed, like in aluminum alloy when it is being quenched, these sort of vacancy loops are formed. Other dislocations are in many other alloy systems, copper also. You can take that if these loops are formed in many nickel based alloys, it has been seen. Then movement of this sort of a partial, but there is a very complex reaction. I don't want to go into the details of it, but in principle you can make out just by looking at the consideration of the bias vectors that this reaction will unfault the loop itself. Okay. Then another one which we consider is that a frank dislocation itself, if we consider, this can split into one with 1 by 6 1 bar 1 0 plus 1 by 6 1 bar 1 2. Okay. This is an interesting one. Energetically, this reaction is, this will be 1 by 18, this is going to be 1 by 6, and this is going to be 1 by 3. Okay. So essentially this is only a very small fraction which it adds. This reaction is energetically favorable, correct? In fact, this is the reaction which is responsible for creation of stacking fault tetrahedra. I am not going to all the details of it, but you take it from me that this sort of reaction, okay, is responsible for a stacking fault tetrahedra is to be generated during deformation. Because in many irradiated materials, okay, as well as in many silicon systems, people have seen stacking fault tetrahedra forming in deformed samples. So this is just to give a flavor of how in an electron microscope the faulted microstructure will look like. Is that here if we look at it, okay, this is all the dislocations are split into partials. So we can see the fringes corresponding to stacking faults, okay. But at the end of it here we can see a partial, okay, which is also visible. In these cases, in this particular one, the partial is visible only on this side of it, okay. That all depends upon what is the sort of bias vector which you have used to image them. That imaging condition decides whether the fault is visible or the partials are visible or both are visible. They all depend upon the different type of G vector which we use to image them, okay. Here what we are trying to show is how in 3 dimensions, okay, part of the sample is to scout how the faults will be lying on those planes, okay, generating stacking fault between them. This is another example where we consider where the stacking fault itself has formed a constriction to a perfect screw, okay. This constriction only, okay, can cross-link, because then when it has become a perfect screw dislocation, if some obstruction is there to a passage of the dislocation, then it can cross-link, okay. That is what essentially is being shown here. The constricted part has cross-link and it has again split into a partial, okay. Okay. Now let us look at Thompson tetrahedron. Because why I said Thompson tetrahedron is important is that here when we wrote many of these reactions, okay, that is a perfect dislocation splits into a partial, okay. Suppose we apply a load to the sample, okay, in which direction, which one has to be the perfect dislocation, because we have seen that one direction of a partial creates an intrinsic stacking fault, another direction creates movement, creates a high energy fault, okay. So if so we have to be very careful about which is going to be the leading partial. Which partial, the moment of it generates a striking fault, which is the one which follows it, okay, the trailing partial, which closes the fault, and they move together. Okay. This has to be fixed correctly whenever we assign Burgess vectors to the partials which are generating striking faults. For this sort of an arrangement is good. Not only that, when we consider many deformation processes, okay, this Thompson tetrahedron is extremely useful to visualize it. These are all the two aspects which I wanted to emphasize in this lecture. This is an FCC lattice. In this FCC lattice, this is the origin. I had just shown the other atom positions which are close packed directions which are adjacent to this. Okay. If we join all these vectors, okay, together, that forms a tetrahedron. You look at this tetrahedron joined by, in this tetrahedron, the points which are A, B, C which are joined together. This surface is nothing but a slip plane, and ADC is another slip plane. So this tetrahedron, when we look at it, it represents nothing but all the slip planes. Okay, the surface represents the slip plane. A magnified view of the same is being shown here. Okay. Now, these vectors, that all the edges represent perfect translation vectors, because from here to here or here to here or from here to here, that represents half 110 Burgess vectors. So they represent perfect translation vectors. So edges represent perfect translation vectors. Okay. And the center of each of the surface, if we consider, okay, and join them to these A, B and C here, okay, and name it as delta, because opposite to D, we are naming it as a Greek letter delta. Then these form the partials of the type 1 by 1, 1, 2 bar type. Okay. These are all, so all these represents partial dislocations. Then from this D to this delta, if I look at it, that vector will represent 1 by 3, 1, 1, 1 type. So essentially, in this this tetrahedra, the surfaces represent slip plane, edges represent perfect translation vectors. From the face center to all the edges, they represent the partial vectors. Okay, vector of partial dislocations, and then the corner to the opposite face center, that vector represents the frank partials. So almost all the dislocations which are there can be represented in this one structure itself. Okay. Then the other convention which is followed is that if I look at this structure from outside, okay, that from outside I am looking into this structure, and if by a movement of a translation vector here, okay, we generate that is move atoms from one position to another position, which are atoms sitting on the next layer. Okay. Those movements will be represented by some vectors. Okay. How exactly is done, now we will describe, but before we go into it, let us consider that this tetrahedra is easy to visualize, it is good, but if you wanted to work with and find out the reactions, looking at the tetrahedra is going to be understanding it is very difficult. Okay. What we do it is that at the corner, this D, we open out, and then when we open it out, this will become like a plane surface, correct? So that is what essentially is being drawn here. That is, from the D, we cut it like this, all the surfaces, and open it into a flat surface. Then this is how the Thompson tetrahedron will appear. And here all the line directions, vectors, everything is being marked. Okay. And this is A to delta, this is the reaction. And what happens is, suppose we look at AB, okay, this vector. AB can be written as A delta plus delta B. This is how vectorially we will be representing it. Okay, correct. This delta B is essentially, if you look at it, is the movement when we look from outside onto this layer, because the atom is, there are another atoms which are going to sit on this surface and this surface as well as on this surface. Okay. The projection of an atom on this surface will be here. That will be moved from here to a direction from delta B. If it is moved, that will create an intrinsic striking fault. That is, the convention essentially is that if we are looking into the Thompson tetrahedron from outside and displacements are being done on the atoms outside of this surface, okay, then delta B, delta C and delta A will generate intrinsic striking fault. Okay. Suppose I look at the structure from outside to, but suppose the movement of the atom is taking place inside of this tetrahedron. That is equivalent to looking at an atom planes which is below this surface. The below this surface, if we look at it, then exactly the opposite will take place. A delta, B delta and C delta will generate an intrinsic striking fault in those cases. Both the cases intrinsic striking faults are created, but in one case, if it is above, it is going to be delta B, delta A, delta C, and if the vector, the movement of the partial moves atoms below this plane ABC, then it will generate, that is to create intrinsic striking fault, the Burgess vector of the partial will be A delta, B delta and C delta. Okay. Actually, this will become very clear if you look at it. What I have done here is I have just shown only that one part of that ABC phase of the tetrahedron which is being shown. Okay. You look at this atom, this is A atom, this is the atom which is on this layer above it. If it is moved from here to here, this will generate an intrinsic striking fault, or from here to here, or from here to here. That corresponds to from this center delta to A, delta to B, delta to C. Now it will be very clear. Now we look at an atom, this is if it is A and this is B and the C atom has to come here, but below A atom a C atom will be there at this position, correct? That atom, how it will be shifting. So this C atom, if it is shifting in that position, it can shift from here to here, or from here to here, or from here to here, which is opposite to from here to here, correct, on the top layer. That will create an intrinsic striking fault. So that means A delta, B delta and C delta will create intrinsic striking fault. So the convention which we do follow is that if we consider moment of atoms on the top layer, then in this reaction which we have written, delta B is the one which is going to create the intrinsic striking fault. So if we have a dislocation, right, we can write in. Okay. That is a dislocation which has a, I will just join together. So this is a perfect dislocation. Okay. This has split into a partial. Okay. And where to fix these two vectors is what it is. I apply a stress in this direction. This Burgess vector B is in this direction. Okay, you assume this of the perfect dislocation. Then you know that the force on this dislocation is always, if it's an edge type of a dislocation, the force is going to act in this direction. So the dislocation will move in this direction. That means that as the dislocation moves, which has split into partial, the first dislocation should create intrinsic stacking fault. That means that the delta B should come here and A delta will come here. This is how it is being placed. Clear? If the same reaction we consider that it is taking place not on the top layer, at the bottom layer, okay, then what will happen is that in such a case, so that this A delta will be placed here, delta B will be placed here, because the bottom layer is where the deformation is occurring and the direction in which it is being moving is in that same direction. Understand that? This can be fixed looking at Thompson Tetrahedron, following this logic very easily. Is it clear? That is exactly what is being shown here. We have considered a vector CB that changes into C delta plus delta B. Okay. You can see that here in this case, okay, this is the direction of the stress, okay, and the dislocation moment is in this direction, then the delta B will become the vector generating an intrinsic stacking fault. In the other case where this is the direction of the Burgess vector, okay, now you can see that B delta becomes the leading one and delta C becomes the trailing one. Okay. Is it clear? Okay. Essentially the same thing is being shown here schematically. Now you can consider that C, okay, but I will not spend time on it. Okay. I had shown it in this slide also in a different way, how we can consider these various reactions. That is, the if we view from outside the tetrahedron, delta B will be the leading partial, this will be the trailing partial. The other way round, as I mentioned, A delta will be the leading partial. That is, when we view from inside of the tetrahedron or from there, we look at the movement which is taking place below the surface of the tetrahedron. Okay. Then A delta will create an intrinsic stacking fault and that will be the leading partial. Okay. Just I am showing one or two examples to illustrate why it is very important in visualization, because on this is a tetrahedron which is being shown where an edge dislocation has split into a partial. Okay. So where the BC is the Burgess vector of the dislocation. So if BC is the Burgess vector, it splits into B delta plus delta C. This reaction, if you look at it, is all taking place within the tetrahedron. That means that B delta will create intrinsic stacking fault. Okay. So B delta is being shown here and delta C is the one which is trailing. That's what is being marked also. B delta is the leading partial and delta C is the trailing partial. Okay. Similar thing happens for the screw dislocation also. We can show how the leading and the trailing partials, okay, are being placed. Okay. This, if you look carefully, you will understand it. Okay. Here I had considered where the sense of direction has been changed, then the leading partials also change. Here the C delta is the leading partial, here B delta is the leading partial. Okay. But both the dislocations, the splitting of the dislocations into partial and the movement of the partials are taking place within the tetrahedron. So either C delta or B delta one can create, has to be the leading partial. You understand that? Okay. Especially the Lamar-Carter lock which we considered, that we can understand if we look at it very easily. Okay. You see that this is one plane in which that ABC plane where the dislocation which is split into partial, they are moving. This is another plane in which the dislocations which are split into partials, they are moving. And if you consider here this B delta and gamma B, when they join together, okay, this will generate gamma B plus B delta will generate nothing but gamma delta. By vectorial addition it will turn out to be, okay. And this is what essentially is nothing but where we have written this reaction. That is this Lamarck-Cottrell log 1/6, that is gamma delta, its magnitude is 1/6 110. That is a Burgess vector, okay. And now, and this also becomes very clear because otherwise, okay, visualization is very difficult. Like previously the way I explained, okay, you are not able to visualize it. Now we can visualize all the slip planes, all the splitting of the dislocations to partial in the different planes, how they are moving. Now they have moved and joined. This is delta C, okay, which is remained here, and this is the stair rod, okay. This is the other part of the dislocation. Now you can visualize very clearly, see that this is a stair rod which is forming, correct? Another case which we can consider it is, what we considered so far was essentially dislocations in two planes, perfect dislocation which are split into partial. When the strike fault energy is low, the dislocation itself will be curved, right? One part will be lying on one plane, another might have cross slip, and then it might have moved into a parallel slip plane. Such cases, and if the dislocation split into partial, that is what is being considered. You consider this case, the Burgess vector is the same BC for these two segments. This dislocation essentially will have a Burgess vector AD, okay. This is how the dislocation looks like, perfect dislocation, because in this Thompson tetrahedron it is easy to visualize. Now this is split into partial, forming a constriction, okay. Then here when this has separated, okay, it has just formed a stair rod of dislocation, and the other part of the stair rod of dislocations are there. Then this part of it also, parallel slip plane, it has split into partials. Now when you look at it, you can visualize that in 3 dimension how these dislocations are lying. That visual feeling we get it when we use Thompson tetrahedron to write or draw all the dislocation reactions. That is one advantage of using Thompson tetrahedron. Okay. There is another picture which you can see that where from this node and it has just formed an extended node and formed 2 more of these stair rod of dislocations. So all these things, now you look at it physically, how this splitting looks like, you are able to visualize it, correct? All these things we are able to do it because we are using a Thompson tetrahedron, and on which all the dislocation reactions we are marking it. This is one great advantage in using Thompson tetrahedron. Okay. All reactions look very complicated, okay, but you can visualize very easily. In fact, if in this one I look in this direction, assume that in the TEM I am looking at this sort of a reaction which has occurred, okay, this is the beam direction. So the projection of this is what you are going to see on the image, right? What you see in an image is a projection, but the Thompson tetrahedron gives you a 3-dimensional visualization as it appears, okay. So that's why it's a very powerful one. And in fact, you might have noticed that in most of the books, instead of writing the Burgess vectors of the dislocations, you will always find that they write like A delta, B delta. This is the nomenclature with which it is being written. The Thompson tetrahedron is being, this nomenclature is routinely being used to represent different perfect or partial dislocations, okay. So I have tried to give a brief idea of the splitting of dislocations into partials, what are the type of partials which they can form, and what is the need for Thompson tetrahedra, because you can understand that using Thompson tetrahedra we are able to fix where in which direction the leading dislocation has to be, out of the two dislocation which will be the leading, which is the partial. All these things we can understand, okay, and place them when we do it on a Thompson tetrahedron, using the Thompson tetrahedron. Okay. I will stop here now. Okay. In the next class, we will look into dislocations in other structures like BCC and HCP also we will try to look at it.